Hello and welcome to week 2, lecture 3, where we're going to work on a few force examples. The ones we're going to do are sample problems 3-4, 3-5, and 3-7. Okay, we're going to start with 3-4. A worker W is pushing a packing crate of mass M1 equals 4.2 kilograms. In front of the crate is a second crate of mass M2 equals 1.4 kilograms. Both crates slide across the floor without friction. The worker pushes crate 1 with a force P1W of 3 newtons. Find the accelerations of the crates and the force exerted by crate 1 on crate 2. Okay, so first let's do our knowns and unknowns. No. Okay, well, we have mass of crate 1 is 4.2 kilograms. Mass of crate 2 is 1.4 kilograms. And the force of the push, which is given by a P1W, is 3 newtons. I think that's all that we know. Let's list some unknowns. We don't know acceleration 1 or acceleration 2. We don't know the force on 1/2 or the force on 2/1. Okay, now let's draw our situation really quick. Okay, we have our big block, which is mass 1, or big crate, excuse me, and then our smaller crate, which is mass 2. Then we have our worker pushing it with really long arms. Sorry about that. Okay, now time for free body diagram. Oops. So here is our x-axis, and I'm putting the y, but again, we're not using it right now. Plus y plus x. So this is going to be for mass 1. And let's see. Mass 1 has a pushing force, the pushing force from the worker, which is again P1W. And then it also has a force from block 2. So on a crate 1 from crate 2. Yep. Then we want to do the same thing for crate 2. Positive y direction, positive x direction. Okay. And crate 2 just has the one force on it from the force on crate 2 from crate 1. These are all vectors also. Okay. Nice. Next up is using Newton's second law to get some equations. So remember, Newton's second law is the sum of forces is mass times acceleration. So let's do that for each crate. Crate 1, mass 1, acceleration 1. Okay, now this is a little bit easier to show you what I was talking about at the beginning of last lecture with that example, because we only had one force, so I couldn't really show you what I meant entirely. But now we have two forces. So this is how we do this. Normally a summation just means the forces added together, but forces are vectors, so we have to take into account their direction. So the push force, P1W, is in the positive x direction, it's positive. But force, the other force on crate 1 from crate 2 is negative because it's in the negative x direction. So that's where we put that negative sign. 1, 2. And it's no longer a vector in that equation because we've included the direction. Okay, and then the net force for crate 2, mass 2, acceleration 2, and that just equals the force on crate 2 from crate 1. And that's positive because it's in the positive x direction. Okay, and there's a few things to note First of all, these crates are in contact with each other, and when objects are in contact with each other and maintain that contact, they have the same acceleration. So acceleration 1 equals acceleration 2, and we're just going to call it A for acceleration. The other thing is last lecture you learned third law pairs, action-reaction pairs, and that is what these two forces are. They're action-reaction pairs. So vector 1, 2 is negative of vector 2, 1. But I just said in our equations, they're not vectors anymore because I took the sign into account already. So in that case, when they're not vectors, they're just equal because it's the magnitude. Okay. So that helps us out. It simplifies our equation some. So let's take a look at what that does. So we still have mass 1, but times acceleration. And then we have the push force minus force 1, 2. And then we have mass 2 times just acceleration. And then force 2, 1. And remember, these two forces are the same. So we can actually just plug this in to that equation. Which is what we're going to do. So we have mass 1 acceleration equals the pushing force minus, now this is where I plug in, mass 2 acceleration. Okay, and the thing we're trying to solve for first, because I'd asked for it, is the acceleration, which is the same acceleration, we covered that part. And then we want to know the force. But first we'll do the acceleration. So now I just add m2 acceleration to both sides. M1 acceleration plus M2 acceleration equals the pushing force. And then I like to factor out the like terms. So acceleration equals mass 1 plus mass 2. And actually you have to solve for it. But in general, I will do that a lot, just as a heads up. And then we divide mass 1 plus mass 2 on both sides. So we have pushing force divided by the masses added together. And that is our acceleration. And so the pushing force is, I forgot, 3 newtons. And then our masses are 4.2 kilograms plus 1.4 kilograms. This gives us an acceleration of 0.54 meters per second squared. So that's the acceleration that the problem asked for. The next part is the force. But again, these forces are the same. So we only have to solve for one of them. And let's look at that equation right there. F21 equals m2 times acceleration. Look at that. We know this, and we want that. Perfect. Let's plug in our numbers. Mass 2 is 1.4 kilograms. The acceleration is 0.54 meters per second squared. And this gives us a force of 0.76 newtons as the force between the two crates. Cool. So that's the first problem. Let's go back over what we did really quickly, and we'll move on to the next one. We went over our knowns. We didn't have a ton. That worked out fine. Then we drew a lovely picture of a person with giant arms. And then we drew our free body diagrams, and I did not label that this was for mass 2. And then we took our equations from our free body diagrams, and I'm just going to touch on this again because this is something I really want you guys to get out of doing these examples, is how to go from a free body diagram to these sum of force equations. So it's literally just reading what you did off of the free body diagram. So, okay, we have our pushing force, that's in the positive x direction. So put that there. And then we have this other force that's in the negative x direction. That's why we have this negative sign. And then we put that force here. Okay, that's the important part. And that equals mass times acceleration because of Newton's second law. So over here for mass 2, there's only one force, so we just set that equal to mass times acceleration. And then I said that acceleration of two objects in contact is the same. So A1 equals A2, and we're just calling that A. And then those two forces, force 1, 2, and force 2, 1, are an action-reaction pair of forces, which means the vectors are in opposite directions, but the magnitudes, so that's what's happening here. The vectors, it's negative. The magnitudes, it's the same. Okay, then we took our equations, we plugged the action-reaction force from one equation to the other. We solved for acceleration and got 0.54 meters per second squared. And then we plugged that in to solve for the force between the two crates. Okay. Next up, excuse me, we have a flatbed cart of mass B, 360 kilograms, rolls on frictionless wheels. Resting on the cart is a box of mass B, 150 kilograms. The box can slide on the cart, but each exerts a force due to friction on the other during the sliding. When the worker pulls on the box with force FBW, both the box and the cart move forward, but the box moves faster than the cart because the frictional force is not strong enough to prevent the box from sliding forward on the cart. An observer measures the magnitude of the accelerations to be 1 meter per second squared for the box and 0.167 meters per second squared for the cart. So we're asked to find the friction force between the box and the cart and the force the worker is exerting on the box. So knowns and unknowns. Let's see. We have our masses. Mass of the cart is 360 kilograms. Mass of the box is 150 kilograms. Yep. And then we just have the two accelerations. So acceleration of the cart is 1 meter per second squared. And acceleration of the, oh, I'm sorry, I have that wrong. That's acceleration of the box. Acceleration of the cart is 0.167 meters per second squared. So this time, the accelerations are not the same because they don't move together. The box slides on the cart. So that's why we have two different accelerations. And our unknowns are the forces. Let's see, the force on the box from the worker, and then friction is given by this lowercase f. That's what I'm going to use. But I'm still going to give it the subscript of, well, it's between the two, so we'll just say box and cart. Okay, picture time. Draw our situation. The ground, the wheels, they're uneven, I'm sorry. The box on top of the cart, a rope attached to the cart, worker pulling on the rope. There we go. Now let's do our free body diagrams. This is for the box. So the box has the force from the worker. So that, oh, geez. There we go. Force on box from worker. And then we have that friction force between the two surfaces. And that is the force on the box from the cart. So I apologize if I say crate. I keep thinking it's crate because box and crate. So sorry if that happens. Then we do the same thing for the cart. and the cart just has the friction force between the two, between the box and the cart. So that, I'm trying to make it the same size, though it's not quite the same size. Curly F, C, B. Okay, so we have our forces. Now we do that same thing again where we get our equation. So the sum of forces for the box is the mass of the box times its acceleration. And that is the force on the box from the worker, which is in the positive x direction, minus the friction force between the box and the cart, because that's in the negative x direction. And we do the same thing for the cart, mass of the cart, acceleration of the cart, but it only has the one force, the friction force. Okay, cool. So we want to find, yeah, both of the forces. So let's check out our equations. One thing to remember is that the vector, which by the way, these should all be vectors. I apologize for not giving them vector hats. The vector of these forces are equal and opposite. Oops. BB. Great. By, see, I called it great. Cart by the box. Okay, but then the magnitudes are equal. And again, this is magnitude, so we don't need to mess with the sign. We've already factored the sign in. But actually, that doesn't even matter because we have this equation here and we know this and we want to know that force between them. So we'll just solve that equation. Easy. So we have mass of the cart, acceleration of the cart equals this force between the cart and the box. Let's plug in our numbers, but I can't, yeah, 360 kilograms for the cart. The acceleration of the cart is 0.167 meters per second squared. Is the force, and that gives us the force between the two, the friction force between them is 60 newtons. Okay. Then if we look back at this equation here, so the other thing we want is this force, but now we know this and we already knew these, so we can just use that equation to solve for the force. Let's see, mass of the box, acceleration of the box equals the force on the box from the worker minus the friction force between the box and the crate. Cool, and we'll just add that friction force to both sides to get the other force by itself. Yeah. And we get mass of the box, acceleration of the box plus the friction force equals the force on the box from the worker, which is what we want to know. So the mass of the box is 150 kilograms. The acceleration is 1 meter per second squared. And then we just found 60 newtons for that force. And this gives us, I did the calculation already. There we go. 210 newtons as the force that the worker applies to the box, or the force on the box from the worker. So we'll go back through that really quickly again too. We wrote down our knowns and unknowns. This time there were two different accelerations because the box and the cart do not move together like the box slides on the cart. So they have different acceleration. We drew the situation and then we drew our free body diagrams. From our free body diagrams, we got our equations by just reading our free body diagrams. The force that the worker applies to the box is in the positive x direction, and the force that the friction force between the box and the cart is in the negative x direction. So we just subtract one from the other. We also noted that those two friction forces are the same or at least equal magnitude. But we didn't need to worry about that at first because we had this equation right here that had two things we knew and one thing we didn't. So we just solved that. That's where we got 60 newtons. And then we took that and plugged it into the other force equation, rearranged it a little bit, and got 210 newtons as the force on the box from the worker. Okay, last one. So, a passenger P of mass 72.2 kilograms is riding in an elevator while standing on a platform scale, which is essentially a calibrated spring scale that reads the upward force, force of the passenger on the scale, exerted on the passenger by the scale. The situation would be exactly the same if the passenger was hanging from a spring scale, just so you know. We want to know, what does the scale read when the elevator cab is A, descending with constant velocity, or B, ascending with an acceleration of 3.2 meters per second squared? So let's write down our knowns and unknowns. So we have the mass of the passenger, 72.2, kilograms. And we have two different situations. I'm just going to give them the subscripts A and B since they're part A and part B. So for part A, the acceleration is 0 because it's constant velocity. Remember, that's what constant velocity means. 0 meters per second squared. And then for B, they give us the acceleration of 3.20 meters per second squared. Okay, and then our unknowns. We don't know these forces between the person and or passenger, excuse me, that's what the P stands for, and the scale. So let's draw our situation. We have our elevator. Elevator has this cable, we have this scale, and we have our passenger on the scale. Cool. Now we're gonna draw the free body diagrams. I'm gonna just draw both of them for situation A and situation B. And this is the free body diagram of the passenger. So this is for A. And in this case, so the forces acting on the passenger are the passenger's weight force going down, and then the force on the passenger from the scale is going up. And since the acceleration here is 0, that means the net force is also 0. So these vectors should be the same size. Cool. Now for situation B, maybe I'll use a different color. B. So in this case, we still have the weight force. But so I told you the value of the acceleration, but I didn't mention that it's up because, so one way we want to think about acceleration, is how it's affecting the velocity. So ascending means going up. So the velocity is in the positive y direction, which is this. And, if it's the acceleration is also moving in that direction, which means it's positive. If, for example, it was traveling up and slowing down, then the acceleration would be negative, pointing in the opposite direction. So this is the weight force. Oops. Pretend it is the same size vector as the one for part A. That was just my bad. They should be the same size. And then the force on the person from the passenger from the scale should be bigger than the weight force because the net force needs to point in the same direction as the acceleration. Okay, now we'll do these parts one at a time. So for A, the sum of forces is mass times acceleration, but this is 0. The acceleration is 0. So we have the force in the positive y direction, which is the force on the passenger from the scale, minus the weight force. So we find here that the force on the passenger from the scale equals the weight force, and the weight force is mass times acceleration due to gravity. So this is the mass of the passenger, 72.2 kilograms, times 9.8 meters per second squared, and that is 708 newtons as the force in situation A. And then in B, the sum of forces is mass times acceleration. There's acceleration this time. But then the rest of the equation is the same as a weapon part A, where it's the force on the passenger from the scale minus the weight of the passenger. And we are solving for this value, so we'll just add the weight to both sides. So mass times acceleration plus the weight is equal to the force on the passenger from the scale. And then I'm going to plug in, because weight is mass times acceleration due to gravity. So I'm going to plug that in. ma plus mg equals the force. And again, like I said, I like to factor things out. So it's totally unnecessary at this point, but I'm going to do it now when it's not going to throw you off as much. So I'm just factoring the math out to simplify things for myself so I don't have to plug it in twice when I'm plugging in my numbers. Okay, so let's plug in our numbers. 72.2 kilograms times the acceleration is 3.2 meters per second squared plus 9.8 meters per second squared. And this gives us the force of 939 newtons. So that's a lot bigger than what the passenger feels when the elevator is not accelerating. Now I want to do one more example that wasn't actually in the question, which is traveling up and slowing down. And slowing, which means velocity up or positive, acceleration in the opposite direction or negative. And we're just going to use the same acceleration, just keep it simple. So we have to draw this free body diagram. Okay. So this time our acceleration is pointing down. So our net force also needs to point down. So that means the downward vector should be bigger. So we have the weight force, and then we have the force on the passenger from the scale. And that is smaller than the weight force. And then we do our sum of forces, not with the eraser. Sum of forces equals mass times negative acceleration. So this is where I remember to include the sign of the acceleration or the direction of it. As I plug it in, just like I do with the forces, I do that with the acceleration in this equation too. And then we have the force that's in the positive y minus the force in the negative y direction. And we still want this force, so we'll just add the weight to both sides, and we end up with the weight minus mass times acceleration equals the force, and that is mg minus ma equals the force. And one more time, factor out the mass minus, or g minus a equals the force. So 72.2 kilograms times 9.8 meters per second squared minus 3.20 meters per second squared. This gives us the force on the passenger from the scale of 477 newtons. So what we see is maybe I'll write this on the next page, is when the elevator is moving up with no acceleration, which is actually more important than whether it's moving up or not. The force the passenger feels from the scale and also the reading on the scale is just equal to the actual value of the passenger's weight. But then when it's moving up and speeding up, then we see that the force that the passenger feels from the scale or the value on the scale is actually greater than the weight of the passenger. And finally, when we're moving up and slowing down, we see that the scale reads a value that is less than the passenger's weight. Okay, those are the examples for today. And yeah, I hope you have a great week too.